Hey guys, so today we're going to start a new lesson called Oxidation Numbers. Alright, so oxidation numbers. Numbers called oxidation numbers can be assigned to atoms in order to keep track of electron distribution in molecular as well as ionic compounds. So basically, when we start off with oxidation numbers, some of you will notice that a lot of oxidation numbers are very similar to the charges of different atoms. But the truth is, oxidation numbers are not always equal to the charge of the atom. They are sometimes a little bit different depending on the situation that we're looking at. So what an oxidation number basically describes is where are the charges found in a compound? Where can I find electrons within a compound? So if I'm looking at an ionic compound, I can see that there's a positive charge on sodium and a negative charge on chlorine. But when I get into molecular compounds or covalent compounds where the overall compound has a charge or the overall compound has no charge, we don't really know exactly where those electrons can be found within that overall compound, because obviously some atoms hold electrons closer to themselves than others. Okay? So the charges on the ions in an ionic compound reflect the electron distribution of the compound. So remember, oxidation numbers are just the electron distribution within the compound. So when I look at this compound, sodium chloride, I can clearly see that the sodium has a positive and the chlorine has an extra electron, which is a negative charge, right? So in order to indicate the general distribution of electrons among the bonded atoms in the molecular compound or a polyatomic ion, oxidation numbers are assigned to atoms. So basically, when I want to find out where the electrons are distributed within a molecular compound, I need to actually find oxidation numbers. And there are several rules that we're going to go through today, which we're going to be applying for the rest of the week. Okay, so today is a very important day. You have to get these rules, otherwise you're going to be struggling a little bit for the rest of the week. All right, so the whole idea here is, you guys remember, in a covalent compound, there are electrons being shared between more than one atom, right? So this hydrogen, it's sharing its electron with the oxygen. However, when I'm looking at this situation, because oxygen has a very high electronegativity, you guys may remember this word from when we talked about trends in the periodic table. When you have a higher electronegativity, that means that you drag electrons closer to yourself. So when I look at this compound, this is obviously water, it's H2O, right? When I look at this compound right here, the electrons are dragged a lot closer to the oxygen, and therefore the oxygen actually has an oxidation state of -2, because it's as if it took the electrons from the hydrogen. So even though they are being shared, they're being held a lot closer to the oxygen. So even though the overall charge of the oxygen is 0, it has a partially negative charge, its oxidation state is -2. Okay? All right, so now, when I'm looking at a compound overall, or the atoms within a compound, if it is a pure compound, for example, oxygen is made up of 2 oxygen atoms, phosphorus is made up of 4 phosphoruses, and sulfur can often be found in this ring shape with 8 sulfurs, right? So in this situation, they are all equal to 0. So they all have an oxidation state of 0. So anytime you get a question where you see a pure compound like Cl2, Br2, O2, N2, just go ahead and put a 0 down, because they have an oxidation state of 0, because they're pure. All right, so the next rule, the more electronegative atom in a binary compound is assigned a negative number equal to the charge that it would have as an ion. Okay, so if I ever had a compound, for example, let's say HF. This is hydrofluoric acid. You guys remember learning about that in the binary acids. In this case, I know that this would be +1, +2, +3, -3, -2, -1. because fluorine is the more electronegative atom, I can just go ahead and automatically assign it with its regular charge. So the more electronegative atom in the compound gets automatically assigned with its regular charge that it would have originally been given, right? All right, so again, now this is a rule that you guys will actually will be easy for you to remember. Fluorine's oxidation number is always, always, always -1. And that's basically because of the rule that we just mentioned above. Fluorine is the most electronegative atom in the periodic table, which means no matter what combination you are ever going to find it in, it is always going to take on its regular charge that it would have taken when it becomes an ion, right? So if fluorine wants to become an ion, it would become -1. And because it is in it's the one with the highest electronegativity, it is always, always, always going to be -1. There's never going to be a situation where it's bound to an atom and that atom steals electrons from fluorine. Fluorine is always going to be more powerful, and it's always going to be the one that steals electrons from the other atom that it's bonded to. Okay? All right, so now we get into oxygen. Oxygen, there are several rules, but however, as soon as you see an oxygen in a compound, you can just come back to this slide and assess the situation that you're dealing with. As a general rule, oxygen is almost always going to have a charge of -2. So if I go back to this periodic table, you guys remember this periodic table right here, right? Oxygen normally has a charge of -2. And remember, oxidation states are not technically charges. They have to do with where the electrons are found. But because oxygen in general has a higher electronegativity, it usually will be stealing electrons from other atoms. And that's why in most cases, oxygen is just going to have a charge of -2. Now, the only time this changes is when oxygen is bound to fluorine. Because when it's bound to fluorine, remember we said fluorine is always going to be the more powerful one. It is always going to be the one that steals the electrons. So in this case, oxygen would not have a charge of -2 because it wouldn't actually have more electrical charge or more electrons attached to it. Okay? So, as a general rule, and in most cases that you're going to see, oxygen will have a charge of -2. The only times where this is not true is when oxygen is found in the form of a peroxide. You guys may have heard of hydrogen peroxide. You probably have some of this in your sink or in your medicine drawer. It's usually used to clean cuts and stuff like that. Basically, hydrogen peroxide usually consists of two oxygens that are bound to each other. Any peroxide atom is going to have oxygens that look like this. So, even though this is not very important for you to know, what you need to know is that there's two electrons shared between them, and when this atom or when this molecule reacts, one electron goes to each side. This is why whenever you see oxygens involved in a peroxide situation, you have to assign each one a charge of -1, not -2, because these two electrons that are shared here are not actually being shared. When the time actually comes for it to react, one electron goes to each oxygen in the compound, right? So anytime you see a name that includes the word peroxide in it, you don't go with -2, you need to go with -1 for each oxygen instead, okay? All right, so in compounds with fluorine, such as OF2, oxygen's oxidation state is +2, okay? This is obviously a huge, very dramatic change, and that's because of what we said earlier. Remember, positive means that you have lost your electrons. Your electrons have left you, and you guys know that oxygen likes to be negative. So the only time that oxygen is going to take on a positive charge is when it's bound to fluorine, and that's because, let's say we have an atom like this. There's a fluorine here and a fluorine there. These fluorines are very, very powerful, and they like to steal electrical charge. So these electrons that are shared between them are actually going to be pulled more towards the fluorines and not towards the oxygen. So while each one of these takes on a charge of -1, this one loses 2 negative charges and it ends up having a charge of +2. Okay? So just remember, oxidation numbers are not necessarily the charge, because in OF2, that's not really how the charge would actually look, but it has to do with where the electrons are actually found. Who are they more close to, right? So when you look at OF2, the electrons are going to be closer to the fluorines and not to the oxygens. All right, hydrogen also has specific rules. So when a hydrogen is bound to a non-metal, so if I have CH4, those are hydrogens that are bound to carbon. Carbon is a non-metal. That means that each one of these hydrogens has an oxidation state of +1, right? Or when I go HCl, H would have a charge of +1 because chlorine is also a non-metal. Anytime you see hydrogen bound to a non-metal, you give it a charge, or an oxidation state, of +1, okay? However, the opposite happens when hydrogen is bound to a metal. So like in this case right here. Here, hydrogen is bound to sodium. Sodium is found right here, and it is clearly a metal, right? In this case, hydrogen has an oxidation state of -1. So this basically means that electrons are being drawn closer towards the hydrogen, while here, electrons are being drawn closer towards the oxygen. Do you get the basic idea? So, remember, when hydrogens are bound to nonmetals, they take on an oxidation state of +1. When they're bound to metals, any of these right here, they take on an oxidation state of -1. All right, so now when I'm assigning oxidation numbers, I can assign an oxidation number to each individual part of the compound, and I can also assign the oxidation number or state of the entire compound overall. And this is going to be important, but it's a very simple concept. So for ammonium, the overall oxidation number of ammonium would be +1, and that comes from this charge. The overall oxidation number of carbonate would be -2, and that comes from this charge. Hydroxide would be -1, phosphate would be -3, sulfate would be -2. Carbon dioxide has no charge, so its overall oxidation number is 0. Sugar or glucose also has no charge overall, which means its overall oxidation number is going to be equal to 0. Okay? So you guys, remember, these are just the basic rules that you have to follow, and it'll become a lot more clear when I show you some more examples of how we're actually going to use these rules. Okay, so oxidation numbers of monoatomic ions are equal to the charge of the ion. So in an ionic compound, when you see a situation where there's a metal bound to a non-metal, you're most likely going to be looking at an ionic compound. In that case, the oxidation number is just going to be the same number as the charge, okay? So lithium would be +1. Like if I'm looking at NaCl, my oxidation number of sodium would be +1 because sodium is right here, and my oxidation number of chlorine would be -1 because chlorine is right there. And overall, these have a charge of 0, and that's why chlorine overall has a charge of 0. Okay? So now I think it's time we should try an example of how we're actually going to be using these rules. And now, of course, you guys, if this was confusing to you, go back and watch the video, and you can, we'll get more into it tomorrow. All right, so now here we have an element that has a uranium and a bunch of fluorines. So if the first thing I want to do is I want to find out the oxidation numbers of everything that I could possibly know. Okay, So let's go ahead and look at the rules. We see uranium and we have a fluorine. Let's see what we've been given. We know that our overall charge has to be equal to the overall charge of the compound, right? The overall charge of this compound is 0. So overall charge equals, overall oxidation number equals to 0, right? Okay, and then let's go ahead and look through the rules and see if there's anything that we can find that will help us. So this talks about hydrogens. Our compound does not contain any hydrogens. This talks about oxygen. We're talking about UF6, which means also we have no oxygens in there. Oh, here we go. Found fluorines. So here it says fluorine has an oxidation number of -1 in all compounds because it's the most electronegative element. So that's useful to us. All right, so let's go here. Fluorine, so we have uranium and we have fluorine. Fluorine has an oxidation number of -1 in any situation. So we know that we have an overall oxidation number of 0. Now we can actually calculate the oxidation number of uranium, because uranium, we would not know its oxidation number because it's not one of those given rules that we should just automatically know. It's something that can change. Remember, different compounds can have different oxidation numbers. So let's go like this. Uranium plus F6 equals 0. Now the reason I did equals 0 is because of this. See that 0 charge right there? That is why we put it equal to 0. Now, if I had a charge of -1 here, then this would end up being -1. But obviously that is not the case. So let's just go back and put our charge as 0. So now uranium is an unknown, but we know that we have 6 charges of -1. This is because we have 6 fluorine atoms, right? Equal to 0. So now we can just we've created our equation. We know that uranium plus 6 times -1, because we have 6 fluorines, is equal to 0. So uranium minus 6 equals 0. And you guys know that to help arrange this, I'm sure some of you can just automatically do this, but if I add a 6 here and I add a 6 here, this 6 will cancel out this one, and you'll get U equals to +6. Okay? So now I found that the oxidation state of fluorine is -1, and that was just a given one. It was automatic, it came from the rules. And the oxidation state of uranium I found to be +6 by using all of this. Now today your quiz is basically only going to cover all of these rules, so you're going to have to go through them a little bit more and really get the idea before you start the quiz. And tomorrow we're going to be doing a lot more examples like this one, okay? Anyways, guys, good luck, and I will see you tomorrow.